This is lesson 2 for chapter 2 in AP College Chemistry. A few more words about the periodic table. And again, of course, we're going to spend a lot more time on it in a later chapter in the book. I think it's chapter 7. But the word periodic table, first of all, the word periodic, means something that has a regularity or a pattern. And again, one of the amazing things about creation is that we see regularities and patterns all over the place. And a regularity or pattern implies that there is a certain amount of time that takes place between the first event and when that event repeats itself. So periodic table means that something occurs periodically. We could talk about the period of the Earth as it rotates on its axis one day, or the period of the Earth as it revolves around the sun, which would be 1 year, or the period of a pendulum, which would be the time it takes for a pendulum to go down and back, or the period of a mass bouncing on a spring, the amount of time it takes to go down to the farthest and then up to the most compressed part of the spring and back. So the word period implies something that occurs on a regular basis. Now, in this case, time has nothing to do with it. It's a matter of certain properties repeating themselves over and over again. Not exactly, but very similarly. And a table, of course, just simply means a presentation, a way of presenting or mapping out or diagramming this information in a logical way. Now, by the way, not all periodic tables have to look like the one that you're used to seeing in your chemistry book or on the wall in a science classroom. There are round periodic tables. There are three-dimensional periodic tables. There's all kinds of interesting periodic tables, but we will be using the most common and standard one that I think is very straightforward and very easy to grasp. But it's far more profound than you might think. Now, the history behind the periodic table I already commented on a little bit earlier. It goes back to Mendeleev, and it goes back to before the beginning of the 20th century. And this word period then means we're looking for a kind of periodicity, something that repeats itself. And again, remember, things that repeat themselves in the same way imply that there is some regularity in the universe, that the universe is not somehow magical, that the universe is not somehow always different, always changing, undependable, never the same from day to day. And these are all reflections of the fact that, as Colossians 1 and Hebrews 1 would tell us, that there is a God who sustains his creation. And because that God is a covenant-keeping and a covenant-making God, he sustains his creation in a way that the things that we study today we can count on tomorrow. That's part of his making a covenant and keeping that covenant with his creation. Now, the way in which Mendeleev created this periodic table, if you can imagine having a stack of note cards, and on each note card he would write the name of an element and the relative mass of that element and as many properties of that element that they knew about, including how that element might combine with other elements like oxygen. And then when he looked at all those note cards, then imagine he organized those note cards like I did when I was a boy and organized baseball cards. Imagine that he organized those note cards from the relative mass of 1 up to the biggest relative mass that he had. And then he began to lay them out on a table like he was playing solitaire or something. And every time he came across a card that had had properties on it very, very similar to an element whose card he had already laid out, he would put that card underneath, creating a column. Later on, this was adjusted to be rows. I'm sorry. We do columns now. He did rows at the time. Every time he came to a new element, that's what it says down here, he started a new row. And so pretty soon he had groups of elements that had very, very similar properties. Now, before we go any further, it's always interesting to know something personal about these scientists. They were all human beings. They were all finite and fallen. They all had particular gifts and talents, just like you do. And they also had some weaknesses and blind spots, just like you do and just like I do. He was the youngest of 14. I don't know if that meant anything. He did live in Siberia, not the most pleasant of environments. But evidently, if you lived in Siberia, you were kind of looked down upon. But his mom did get him into a teacher training college, and he was a teacher and a professor for the greater part of his life. He was looking for an organizing principle. That's what scientists often try to do. They look at lots and lots and lots of things that seem to be related, but you don't know how. And you try to organize them in a way that begins to reveal some underlying organizing principle or principles. He published his work at just prior to when the Civil War broke out in the United States. He did not have all the elements to work with like we do. At the time, he had about 65 of them. He had the brilliance, the genius, to leave gaps and to suggest that some elements would later be discovered to fill in those gaps. And in a few minutes, we'll look at particularly gallium and germanium. Half of the elements that Mendeleev predicted were not found. And this might have been because he did not know much about isotopes or anything like that. So he had some genius, but it wasn't foolproof. So we come down here to how we change from organizing the periodic table according to increasing relative mass, like Mendeleev did, to organizing the periodic table according to the number of protons. And that was the work of Moseley at the turn of the last century. And when Moseley did this work under the auspices of Rutherford, a New Zealander with multiple Nobel Prizes, he used X-rays, and when he shined X-rays at these different elements, he was able to, when he charged these different metals under high voltage, they released X-rays, and he studied those X-rays. And when he studied those X-rays, he realized that the abundance of each individual group of X-rays was related to the positive charge, which of course is the number of protons that was in the nucleus. Now, by the way, Mendeleev knew about aluminum. He knew about indium. He did not know about gallium. So he called this blank spot in his periodic table Eka aluminum, meaning beyond aluminum. Later on, it was discovered in France, and the Latin term for France is Gaul. If you've ever listened to, in Latin, Caesar's first Gallic War account, it begins like this: Gallia est omnis divisa in partes tres. All Gaul, or France, is divided into 3 parts. He also had Eka silicon. He knew about silicon, and he knew about tin, but he did not know about germanium. And this was later discovered in Germany. And that's why it's called that. So that's just a little bit of an example from the periodic table of the process of it coming into being. Now, if I can get this to work right, there we go. He came up with what we call the law of chemical periodicity. The properties of the elements are periodic functions of the atomic number. Now, we now organize this according to groups or families. These are the ones that have similar chemical and physical properties. And that, of course, is because they have a similar electronic arrangement in their electron shells. So the chemical properties are a function of that electronic arrangement. And then he also talked about the periods. One complete period would be what we now call a row going across the periodic table, where every element is different from the previous element with different properties. And then you start a new row when those properties begin to repeat themselves so that similar elements are on the same or in the same group. Another way of categorizing the elements are terms of metals and nonmetals. And as is so often the case in God's creation, we have our nice, neat little categories. But in God's economy, there's always things that just don't fit our nice, neat little categories. They're right somewhere in the middle. Metalloids, for example, or semi-metals, which sometimes have the properties of a metal and sometimes have the properties of a non-metal, often depending on the temperature. And sometimes these things that don't fit our boxes are the most amazing elements of all. For example, silicon now is absolutely essential for computer technology and computer chips. So we have our metals, which are all on the left side, and we have our non-metals on the right side, and here's our semi-metals there. Different authorities and different textbooks might have slightly different numbers of semi-metals. Now, a way of identifying the columns on a periodic table is according to their group number. And there are different ways that these group numbers are specified as well. For example, group 1A, group 2A, and so forth. I don't generally use group numbers. I just look at the periodic table and recognize that 1A is going to have one electron in the outer shell of every element in that column, and group 2A is going to have 2 electrons in the outer shell of every one of those atoms or elements, and so forth. But these different groups have different names. You should know, first column, the alkali metals. Second column, alkali earth metals. Third column is based on aluminum. The fourth column is based upon carbon, but also has silicon in it. So in a sense, carbon is where all of your organic chemistry comes from, and silicon is where all of your rocks and minerals and earth science comes from. An important vocabulary word is an allotrope. You can have a particular element, but in its pure state, it can exist in some very different but distinct forms. And the classic example is always carbon. You can have what is called graphite, which is sheets of carbon. You can have diamond, which is carbon bonded left and right, up and down, in and out in 3 dimensions. So graphite is one of the softest substances naturally occurring, and diamond is one of the hardest substances naturally occurring. And more recently, we discovered amazing geometric shapes, if you will. For example, spheres and tubes, which named after a famous designer architect named Buckminster Fullerene. We just call these buckyballs. And they're kind of like shaped like the climatron down at Shaw's Botanical Gardens. I call it Shaw's Gardens. You probably call it Missouri Botanical Gardens. But if we were to cut this in half, this upper geodesic dome is somewhat like the upper half of a buckyball, but of course an awful lot bigger. And here's the name of that guy. And it's interesting, we're now trying to put atoms or clusters of atoms inside the sphere, or trying to get atoms or clusters of atoms to move through a cylinder made out of carbon atoms. But these are the different allotropes. Another important vocabulary word is the word alloy. An alloy is a mixture of metals, where the two metals would have different melting points. You heat it up hot enough so they both melt, you mix them together, and then you cool it down below the freezing point for both of them. And now you have an alloy. And of course, we talked about pewter and bronze and brass. Rings, jewelry, for example, are often made out of alloys of gold and silver and copper. Group 5, the ones in nitrogen. Nitrogen itself is diatomic. You should remember Brinkelhoff, the elements which are diatomic. That's going to come up all year long, and if you don't memorize them and become confident with them now, you're going to periodically, pardon the pun, lose a point on forgetting to make certain elements that are naturally diatomic and writing them with the subscript of 2. You'll see that on just about every test. Nitrogen fixation is the way in which bacteria in particular are able to take nitrogen out of the atmosphere. Diatomic nitrogen looks like this with that triple bond. It's extremely stable, and it must be for our atmosphere to support as much oxygen that it does. Otherwise, every time you lit a match or made a spark, the whole atmosphere would blow up, and you hate it when that happens. But in God's providence, nitrogen is diatomic with that strong triple bond. It's a difficult bond to break, but there are certain prokaryotes, such as bacteria, single-celled organisms that do not have their DNA in a nuclear membrane, that are able to break that down, turning it into nitrogen compounds, such as nitrates and nitrites and ammonium compounds and ammonia, which can be used as fertilizers, naturally occurring fertilizers, or synthesized fertilizers for plants to take advantage of. Group 6, we've got oxygen, and of course we've got to have oxygen, and we need the percentage that we have or things would not go well with us. And group 7 are the halogens, the salt makers. The salt forming right down there. They all have need one more electron in their outer shell. And then you have the inert gases, which are the least reactive. That's not to say they don't react at all. We actually can make some compounds now out of some of those inert gases. We'll talk more about that in a later chapter. But for the most part, because they don't react with anything, they don't make compounds, and if they don't make compounds, it's hard to discover them, particularly by the fact, because of the fact that they're gaseous as well. We actually discovered helium, for example, in the sun before we ever discovered it several decades later on the Earth. And the word helium comes from the word helios, which is the Greek word for sun. And plants that like to track the sun, such as the sunflower, are called heliotropes. So other words for these noble gases are inert gases or rare gases. And of course, nowadays, when you want to sell your house more and more frequently, you have to have a radon test to make sure there's no radon gas being formed from alpha particles, helium nuclei, through radioactive decay in the Earth's crust, combining with electrons to make some of these, that would make helium gas that would matriculate up through the crust, but also radon gas in the decay chain of some of the radioactive isotopes can accumulate in a well-insulated, closed-in structure like the basement of a house. Then we have the transition elements, which are in between. They're all metals, but we insert them in between the alkali metals and the alkali earth metals, and then the aluminum and nitrogen and oxygen columns. Later on, we're going to talk about these representing the D shell. And then we have the lanthanides and the actinides representing the F shell, which we'll talk about again later. And these are becoming more and more and more important as we develop more and more technologies that require batteries and require special components to operate our smartphones and our computers and lasers and all kinds of other things. And there's a lot of politics that's going on relative to the mining and getting of these rare earth elements. These rare earth elements aren't necessarily rare, but they are hard to get. And sometimes the difficulty in getting them is political more than it is mechanical in terms of the actual mining process. I'm going to stop there right now, and we'll pick up later.